Hi, welcome to this video. Today I will be looking at Unit 3 of the Edexcel exam board. In particular, I'll be covering all the different AS practicals that we have to carry out throughout the year, and also the other three tasks that have to be carried out under exam conditions. First of all, there is a general practical competence, which basically means that each student has to perform a number of experiments during each year, and usually there are no marks for this activity. All that has to be recorded is the date and the title of the practical, and usually this is done by the teacher, so you don't really need to worry about that because the teacher will plan the experiments in your lessons. There are three other subsections which usually have to be done under exam conditions, meaning that you will be given your exam paper, and you can only have your data booklet with you and no other materials. You can have a calculator, but you can't have your textbook or notes. And these are the ones that I will focus on today. So there is the qualitative observation, which is B, out of 14 marks, and usually the focus is on making observations and identifying unknowns. C, which is the quantitative measurement, marked out of 14 marks, and this usually will involve a titration, and the titration can either be acid and base or iodine thiosulfate, or you could also be asked to carry out an enthalpy change experiment. And the final task, D, which is preparation, is marked out of 12 marks and will involve the preparation usually either of a simple or a double salt. So let's look at all of these in detail. Let's start off with the qualitative observation, which is B. So with the qualitative observation, there are four main experiments that you could be asked to carry out. So you could be asked to carry out an observation exercise on 3 inorganic unknowns. You can have also organic compounds, but these will mostly be limited to alkenes and alcohols. Or they could also be halogenalkanes. So most of the time you'll be asked to mix the reagents and then to record any color changes. Remember, sometimes you can have a precipitate forming, so make sure you notice that, and also some of the precipitates can be colored, so make sure you write down the color. So first, when they ask you to record observations, these are some of the things that you may see and be asked to write down. So for example, if there's a color change in the solution, you should be writing down, for example, that colorless solution turns cloudy. So also the formation of a precipitate, as I mentioned. Again, don't forget to write down the color if there is any of the precipitate. You might have a gas being evolved. So again, the best way to say that would be either by writing bubbles of gas or effervescence. You can then be asked to carry out a test on the gas to confirm something. So it could be that you're asked to use damp litmus paper again, so you need to make sure that you're writing down the change. So for example, the gas turned damp red, litmus paper blue. Flame tests, again, I'll cover these. You need to make sure that you know these, and you can identify what anion or cation is responsible for the color of the flame. And also noticing if the reaction is exothermic, endothermic. So if it's exothermic, the test tube might become hot or warm, so make sure to notice that. Endothermic is obviously when the test tube becomes slightly cooler. Let's look at flame tests. So make sure that the wire is clean by dipping it into some concentrated hydrochloric acid and then putting it into the hot part of the Bunsen flame, and then repeat until the flame is not colored. And then you dip the wire into concentrated hydrochloric acid again, and then into the unknown solid, and again into the hot part of the Bunsen flame, and then you should be able to observe a color change if there is one. And these are the most common ones that you may be asked to do. So we have at the bottom here, we have lithium, sodium, potassium, calcium. And in the table above here, you can see the corresponding colors. This table is taken from Edexcel. So, for example, for sodium, it's a yellow flame. For potassium, it will be lilac, which is represented here. Let's look at heating solids and common gases. So you may also be asked to heat a solid, and the most common ones that you will be asked for will be either carbonates, nitrates, or ammonium chloride. Again, remember to state the observation, so there might be melting, sublimation, there might be a giving off of a colorless or brown gas, or you might see some water condensation on the test tube. You can then also be asked to use a glowing splint, and the question is, does it relight? You could also be asked to use lime water if it goes cloudy, or whether there is a precipitate forming. So for example, if you have carbon dioxide, you possibly can have a carbonate from the group 1. Oxygen will probably be a group 1 nitrate, and things like that. And the tests to confirm what kind of gas you have are shown down here. So for example, if you have oxygen, it'll be a colorless gas, which will relight a glowing splint. If you have carbon dioxide, again it's colorless, however it will give a white precipitate with lime water. Ammonia, again, is a colorless gas, but it will turn red litmus paper blue. So again, these are sort of the confirmation tests that you might be asked to carry out in order to confirm what kind of gas is evolving. Nitrogen dioxide is brown, so that's quite easy. Hydrogen, again, is colorless, which will ignite with a pop sound. Hydrogen chloride is steamy fumes, so that's quite easy to spot. Chlorine will be pale green, which will bleach moist litmus paper. Bromine is brown, iodine purple, and water vapor will turn blue cobalt chloride paper pink. So let's look at the addition of dilute acids. So you might be asked to add dilute hydrochloric or sulfuric acids to a solid, and then a gas may be evolved. For example, if you have carbon dioxide, it's most likely to be a carbonate. If you have hydrogen gas, it will be a metal. You also can have the formation of a precipitate. So when you add dilute sodium hydroxide to a solid, and then you can gently warm the test tube, a gas may be evolved, which can be tested with damp red or damp blue litmus paper, or with a glass rod dipping into concentrated hydrochloric acid. So, and these are sort of the observation that you can make. So if you add dilute sodium hydroxide and you have a white precipitate, and then if you add the sodium hydroxide in excess, if the precipitate is insoluble, then you're most likely that you have either magnesium, barium, strontium, or calcium, and so on. So again, you can pause the video and just have a look at this table. You can also be asked to do the same test, but with concentrated sulfuric acid. So this test is used to distinguish between different halides. So the concentrated acid is carefully added to the solid. And again, you must do this in a fume cupboard. And the observations so for example, if you have a chloride, you will see steamy fumes of HCl, and it'll be quite a vigorous reaction. With a bromide, again, you'll also have steamy fumes, brown vapor, and again, it's a vigorous reaction. With iodide, you'll have again steamy fumes, and you can also have a black solid, purple vapor, yellow solid, vigorous reaction, and so on. So these are the products that you should be seeing. Organic compounds that you might be asked to identify. So usually the only types of compounds examined at AS, so for Unit 3, are either hydrocarbons, so either hexane or cyclohexene. Could be alcohols, so primary, secondary, tertiary, and halogenalkanes, so chloro, bromo, and iodoalkanes. test for a carbon-carbon double bond, so to test for an alkene, we would use bromine water and shake it. And if the brown color changes to colorless, and you might also have two layers, that means that we have an alkene, so there is a double bond. You can also test for a double bond with the addition of dilute sulfuric acid and followed by potassium manganate 7. Again, you would shake the test tube and warm. The purple color should go to colorless, which again confirms that you have a carbon-carbon double bond. You might be asked to carry out a combustion. So the unknown will be placed in a crucible lid and then ignited with a lighted splint. So if it burns with a smoky flame, it means that the organic compound is either aromatic or is unsaturated, so it's an alkene. If it burns with a clear flame, it means it's got a saturated low molar mass compound. Let's also look at the test for primary or a secondary alcohol. So this would involve the addition of acidified potassium dichromate, and if the solution goes from orange to green, it means that you have either a primary or a secondary alcohol. With halogenoalkanes, you would usually add warm aqueous sodium or potassium hydroxide, and then you would acidify it with dilute nitric acid and then add aqueous silver nitrate. So after doing those steps, if you have a precipitate, let's say you have a white precipitate, it means you have a chloroalkane. With a cream precipitate, it means you have a bromoalkane, and a yellow, it means you have an iodoalkane. Another test you can do to test for an OH group, so in alcohols which have the OH group, you can add phosphorus chloride, and again you'll see steamy fumes, which is the HCl, and you can also then use damp blue litmus paper and it will turn red. Well, how do you distinguish between primary, secondary, and tertiary alcohols? Well, in this case, you'd add dilute sulfuric acid and aqueous potassium dichromate, and you warm it gently. So if it goes from orange to green, it means it's primary or secondary, and if the solution stays orange, it means that the alcohol is tertiary. This is the secondary test you do to confirm what type of halogenoalkane you have. Also might be given some data from mass spectrometry or infrared. The relative molecular mass of a compound can be obtained from the mass to charge value of the molecular ion, so that would be the highest value of the mass to charge. You also look out for the fragmentation pattern of the spectrum, which can give you very useful information about the structure of the molecule. So for example, down here I've put a mass spectrum of pentane, which contains 5 carbons, and it's an alkane, so there are no double bonds. So for example, this peak here at 29 is most likely to be C2H5, and the way to calculate that would be, we know that carbon is 12, so if we have 2 carbons, it's 24, and then we have 5 hydrogens, which are 1 each, so 24 plus 5 gives us 29, so we can identify this peak as being C2H5, and the same goes for all the other ones. And remember to always put a plus sign or plus charge on any displayed structure, because we are dealing with ions here. So if you're asked to draw something out, always put a plus, because it'll be an ion. You might also be asked to look at some infrared spectroscopy, a powerful and non-destructive technique to get information regarding the covalent bonds within a molecule. And so I've put in a question here, which is from January 2013. Which I think might be quite useful to look at. So here the question is asking us to look at the following reaction schemes. So we have a colorless liquid, S, and the different reactions that it undergoes. And we also are given the infrared spectrum of compound S, as shown here. And these are the different wave number ranges. All this information will either be given to you like here, or it can be found in the data booklet, in the blue data booklet that you'll be allowed to have with you. So what do we know about liquid S? Well, we know that it's 3 carbons, 8 hydrogens, and then it has an O. So at AS level, we have to assume that this is an alcohol. However, we don't know whether it's primary, secondary, or tertiary. So the first question is saying, give the wave number range of the absorption in the infrared spectrum that shows that compound S is an alcohol. So we have to look at this spectrum here. We're not really concerned anything below 1500 because this is known as the fingerprint region, and usually we ignore it because it's very very complicated. So we look at anything that is above 1500. So we know that alcohols have the functional group, which is OH, and we are given this information here. So the OH bond is the alcohol, and the wave range number is from 3750 to 3200. So we can see here 3000. So roughly it should be between here, and we can see that there is a really extreme peak there between 3200 to 3750. So this is the answer for this question. The second question is identify the type of organic compound formed in the reaction of S with phosphorus pentachloride. So again, this is something you would have to know. We're told that the product is a colorless organic liquid, and we can also see the test that the reactions that the X compound undergoes. So we're using ethanol and silver nitrate, so we can kind of guess that this will be something that contains a halogen, because this is the test that we would use to test for an unknown halogen alkane, and it forms a white precipitate. The white precipitate, that means that it contains chlorine, and because the reaction is with chlorine phosphorus pentachloride, it means that we have a halogen alkane, or more specifically a chloroalkane in this case. So then it goes to say compound T does not produce carbon dioxide but added to a solution of sodium carbonate. From this information alone, what can you deduce about compound T? So let's go back and look at compound T here, and we have an alcohol, and we know that primary and secondary alcohols oxidize further, whereas tertiary don't. We can say that it is not a carboxylic acid, or it's not acidic. Let's look at C. So again, here we're given the infrared spectrum of liquid T. So we know that liquid T is not a carboxylic acid, meaning that we don't have a primary alcohol. So they're asking us to look at this infrared spectrum, and the question is, give the wave number range of the absorption of the infrared spectrum that shows that compound T is formed from a secondary alcohol. And again, this is background knowledge. So we know that secondary alcohols, when they oxidize, they go to ketones. So we're basically in this on this diagram here, we're looking for an absorption of a ketone. So again, we would look up either in our data booklet, or we can look here in the actual question. We're actually given the data. So we're looking for a ketone. So we know a ketone has a double bonded oxygen to a carbon, and the absorption is between 720 to 1680. So that is the number that we will be writing here, and we can also see it. This peak here is the one that represents the ketone. Then the next question is asking us to identify the type of organic compound that T is. Well, we know that we have a secondary alcohol, that it's being oxidized, therefore it is a ketone. So this is the answer for this question. Next, they're asking us to draw the skeletal formula of S. So let's look back at our diagram here. So S is our alcohol, and we know that it gets oxidized to a ketone. Therefore, we know that it is a secondary alcohol, and it has 3 carbons. and they're asking us to draw a skeletal formula. Therefore, the answer should look something like this. And remember, because they're asking for the skeletal formula, they're not asking us to draw the displayed formula, which would be like this. And in the end of those lines, we will have the hydrogens. I won't draw them out. So this is not what they're asking for, but this is what the displayed formula would look for. But this is a skeletal formula, so we have a carbon here, and here, and this is our OH group. And we know that this is a secondary alcohol because the carbon that is carrying the OH group has two other carbons attached to it. So that's the answer. Let's look at D. So it says liquid X gives a white precipitate R on warming with aqueous ethanolic solution of silver nitrate. Identify R by name or formula. So we're looking at R. So here we're told that it's a white precipitate, and we have to basically now write what the precipitate is. Well, because we have a silver nitrate, the precipitate will be silver chloride because it is the test for the chloroalkane. So we can either write silver chloride or we can write the formula, which is AgCl. So the next question, describe what you would see if precipitate R was left in sunlight. And again, that's from our knowledge, from our theory, we should know that the precipitate would darken, so it might go grey or black. And the last question is, suggest why an aqueous ethanolic solution of silver nitrate gives a better result in this test than would be obtained by aqueous silver nitrate. The halogenoalkane is more soluble in aqueous ethanol than in water alone. Therefore, ethanol is a better solvent for our compound X. C of Unit 3, which is the quantitative measurement, usually involve tasks using the apparatus to make measurements and then processing the results. You may also be asked to construct a graph, and in this section, usually you can be asked to carry out either an acid and base titration or an iodine sodium thiosulfate titration, or you can be asked to find the enthalpy change of a single reaction or of two reactions, and then to construct a Hess's law diagram to calculate the enthalpy change for a third reaction. So I wanted to quickly look at the apparatus that you will be using. So you might be asked to use a pipette, which usually does one volume, and usually about in my school we have 10 cm cubed or 25 cm cubed, but usually they only have one particular reading. You can be, for the titration, you'll be using a burette. So each volume is read to the nearest 0.05 cubic centimeters. You'll be using a measuring cylinder, so you can have 100 centimeters cubed or 5 centimeters cubed, depending on what you're being asked to do. You'll be also using a balance to weigh a solid, let's say, and usually the readings are done to 0.01 grams. You can be asked to use timers. Again, they usually read to the nearest second, and thermometers for the enthalpy changes. They go from 0 to 100, and you can read up the temperature to the nearest 1 degree. Here I found a couple of pictures of the different pieces of equipment that you'll be using. So let's first look at the pipette, which is shown here. So first of all, when you're using the pipette, you must wash it out with a little of the solution, which you will be putting into it, and usually you then pipette 25 centimeters cubed into a conical flask. Make sure that there are no air bubbles in the stem of the pipette here. So usually it's better to fill it up. So this is the mark up to which you'll be filling. So usually fill it up slightly more, and then let some of the solution run out so that you don't have any air bubbles at the bottom here. Usually it's made out of glass, and you also will have one of these, which is known as a pipette filler. So you can either have this squidgy ball here, or this plastic one here to fill it up. So again, I'm not sure how to, well, I've used them before, but I think it'll be worth watching a video on YouTube maybe to see how to use these. I find these ones much easier to use, but these are equally as good. It's just you have to try them both out and see which one works better for you. Then we have a burette here, which is used for titrations. You've got this lever here which you turn, which then allows whatever is inside the burette to go out of here into your beaker. And so with burettes, again, you must wash them out with the solution that goes into it. You then fill it to just above the 0 mark. So as you can see, it says 25 here, so it's quite long. So 0 is at the top, so you fill it up to 0 with the funnel. And remember, once you've finished filling it, always remove the funnel. And then you let the liquid run out until there is no air in the stem. So again, in the stem here, there might be some air. So make sure you let the air come out before you start the titration. So if you fill it up to 0, that will be your initial level, so it'll be 0.00. But in terms of reading off from a burette, I thought that would be quite a good thing to know, is when you're recording the volume, you have to record the volume from the bottom of the meniscus, and the meniscus is shown here as the sort of curved line. I'd be tempted to read it as 3.20, but the meniscus is actually on the 3rd line, therefore it's very important that you look at the meniscus. And again here, if you were to read from the top line, you would probably get 3.80, when in reality it's actually 3.90. So that's another important thing. So let's talk about accuracy and uncertainty. When you're doing titrations, over half the marks will be awarded for choosing 2 titers that are concordant, meaning that they are within 0.2 between the largest and the smallest. And always record your readings to 2 decimal places, so 24.70 and not as 24.7, as you won't get a mark. So then to calculate, so let's say we have 4 measurements here, and we want to take the mean of those. So again, you just add them all together and divide them by 4. And again here there's a mistake, so you have to write it as 26.50. Choosing your titers that they are within 0.20 centimeters cubed of each other, and you disregard any sort of larger ones, because that's where a lot of the marks come from, just being able to identify the titers that you'll be using for your averaging. You might also be asked to calculate the error in the reading. So to do that, you would do the uncertainty of the equipment divided by the reading times 100. They usually write it on the equipment as, let's say, plus minus 0.5 or plus minus 0.06. So you can use that value divided by your reading times 100, and that will give you the percentage error of that particular piece of equipment that you're using. So for example, here we have a balance that has an uncertainty of 0.01 grams, and we have a reading of 2.64 grams. So then to get the percentage error, we would take the uncertainty, which is this number here, divided by our reading and multiply it by 100%. So we have the percentage error of that particular piece of equipment with how much grams we measured out. Okay, so let's look at a past paper just to get an idea of what type of questions we might be asked. So this is a question paper from January 2012 for Unit 3B. And these papers are good. I mean, they are meant for international centers, so people that can't actually carry out the experiments, but they still have to do an exam on it. So they don't actually carry out the experiments. They're given sort of the details of what is happening, and they have to answer questions on those just to make sure that they're familiar with the different lab techniques. So in this question we have, so let me just read out what the question says. So magnesium carbonate reacts with dilute nitric acid as shown in the equation below. The enthalpy change for this reaction can be determined as follows. So the procedure, we weigh out 3.50 grams of finely powdered magnesium carbonate. We then transfer 50 cm cubed of 2 mole DM-3 nitric acid into a polystyrene cup and record the temperature of the acid. We then add the magnesium carbonate to the nitric acid, stir the mixture, and record the maximum temperature reached. So this is a question on enthalpy, which you might be asked to do. So then we have a table of the results. So we have the initial temperature, which is 21 degrees, and then the final temperature is 29.7. So we have a rise in temperature. Okay. So question A is asking us to explain why the magnesium carbonate used should be finely powdered rather than in lumps. The answer to this would be so that the reaction is faster, so to increase the rate of the reaction, there is less time for cooling. Meaning that, again, so this is what you have to put for that. Then we have BI, calculate the number of moles of magnesium carbonate in 3.50 grams. This is a calculation question. So we're calculating the number of moles of magnesium carbonate. So how do we do that? Well, from our calculations we know that to get the moles we need to divide the mass in grams by the molar mass. So they've given us the masses, so 3.50 grams divided by, and we're also given the molar mass, which is 84. So we divide that by 84, and we get 0.0417 moles. So that is the answer. B2, the volume of dilute nitric acid used contained 0.100 moles. Suggest why this amount is suitable. So basically they're saying that the nitric acid that was used was in excess, and when we add something in excess it's usually to make sure that, so in this case we add the nitric acid in excess to make sure that all of the magnesium carbonate has reacted. Okay, so the next question, CI, it says calculate the heat energy transferred in joules in this reaction between magnesium carbonate and nitric acid. So we are given this expression here. We don't need to learn it, you'll always be given it. So the energy transferred in joules is equal to mass of the solution times the specific heat capacity of the solution times the temperature rise. Okay, and also we are given that the mass of the solution is 50 grams and the specific heat capacity is 4.18. So to get the energy transferred, we need to, mass of the solution is 50 grams, so 50 grams times the specific capacity we're given as 4.18 times the temperature rise. So to get the temperature rise, we need to minus the final temperature from the initial temperature, and this comes out as 8.7 degrees. So when we multiply all of those numbers we should get 1818.3 joules. So that's quite a simple one. So the next question is asking us to calculate the enthalpy change, delta H, for the reaction of 1 mole of magnesium carbonate with nitric acid. And they're asking us to give the answer in kilojoules per mole to 3 significant figures and to include a sign. So delta H, and there is an equation for this. So the previous answer, which is the energy transferred in joules, we need to divide that by the number of moles. So 18.3 divided by the number of moles. The number of moles we calculated here. So the moles of magnesium carbonate. So we have to divide that by 0.0417. When we divide those, we will get 43,597. And this is in joules. Okay, so they're asking us to give the answer in kilojoules. So in order to get this into kilojoules, we need to divide it by 1,000. We then get 43.597. So this is kilojoules per mole. But then they're also asking us to put it to 3 significant figures, which would make it 43 point. So because we have a 9, means this 5 becomes a 6. Again in the same units. And they're also asking us to include a sign. So they're asking us whether this reaction is exothermic or endothermic. And we can determine that by looking at the temperature. So we started off at 21 degrees, and then the temperature, the final temperature, went up to 29.7. Therefore, there was an increase in temperature. The reaction is exothermic, and for an exothermic reaction, the sign is negative. Therefore, that is the answer, minus 43.6 kilojoules per mole. Let's look at the final question. The next question, which says the nitric acid for this experiment could be measured using either a pipette or a measuring cylinder. Give one practical advantage of using each piece of apparatus. Okay, so a pipette is, as we saw from the previous slide, is the glass rod with a pipette filler. So the advantage of using a pipette is that it's very accurate, very precise as compared to a measuring cylinder. And another advantage of a measuring cylinder is that it's faster and it's easier to use, because with a pipette, as I said, you have to use the pipette filler, which can be a bit, if you haven't used one before, it can be a bit fiddly, but it's more precise. So these are the sort of points you could be putting down for that question. May 2011, again, Unit 3B, which covers which again is usually used for international centers, because they don't have the facilities to carry them out. But it's quite good. If you go on the Edexcel website, you can find all the exam papers for that, and they will help a lot in your preparation for your practicals. So in this question, we have an experiment was carried out to determine the concentration of a solution of potassium iodate. So this is a titration. So again, I'm not going to read out the procedure. You can do that in your own time. We're given 2 equations, and here are the results. So we have 3 titrations. We have the initial reading and the final reading, and then we have so you minus these 2 and you get your volume. So question 1 asks us to look at, it says which 2 titrations should be used to calculate the mean or the average titer. Explain your answer. And we are given, always look at the marks, because that gives you sort of information of how many points you're meant to say. So it says which 2 titrations should be used. So we remember that. So these are the different so we have 3. 2510, 2430, and 2410. And remember what I said previously is that when choosing which titers to use, we have to make sure that they're within 0.20 of each other. So we can definitely see that 25 is out because it's way bigger. Therefore, we would be using titration number 2 and 3. And the explanation we would give is that they agree within plus or minus 0.2 centimeters cubed. So that's our answer. So then the next question is asking us to calculate the mean titer. So since we know that we've chosen 2 and 3, it's quite easy. 2430 plus 2410 divided by 2 will give us 2420. And remember to always put it to 2 decimal places. So that's our mean titer. The next question is asking to look at, so the question says, the sodium thiosulfate solution used in the titration has a concentration of 0.100 mole per decimeter. Calculate the number of moles of sodium thiosulfate in the mean titer. So to get the moles, we will use the other equation because we know the concentration and we also know the volume from the previous questions. So in this case we have to multiply the concentration, so 0.100 times the volume. But the volume we have here is in centimeters cubed, but we need it to be in decimeters cubed. So we have to divide the volume by 1000, which will give us the decimeters cubed. So then the moles we get will be 0.00242. So that is the moles of sodium thiosulfate in this titer here. So then the next question is asking us to use equation 2, which is this equation here, to calculate the number of moles of iodine, I2, which is here, that reacted with the number of moles of sodium thiosulfate you have calculated in the question above. So we basically have to look at the stoichiometry here. So we have one iodine and we have 2 moles, well, there's one here, and we have 2 of sodium thiosulfate. So we know the moles of sodium thiosulfate, but because the ratio is 1 to 2, so therefore to get the moles of iodine, we have to divide the moles that we calculated. So this value here, we have to divide it by 2 to get the moles of iodine. So 0.00242 divided by 2 gives us 0.0012. So that is the moles of iodine. And then the next question is saying, use your answers to part A4, which is this one, and equation 1. So now they're asking us to use this equation here to calculate the number of moles of iodate 5 ions in 25 centimeters of solution. So again, we can double check 1 mark, so it shouldn't be too difficult. So we know we have to use the answer to part 4, so we have to use the moles of iodine. So again, they're asking us to look at the sort of the balanced equation. So we know the moles of iodine, and they're not asking us to look to find out the moles of iodate ions, which are here. So again, in this case, we have 3 moles. So we have 3. The ratio is 3 to 1. Therefore, to get the moles of iodate 5 ions, we need to divide 0.0012, which is the moles of iodine, by 3, which will give us 0.000403. And then the last question, it says, use your answers to A5, which is this one, to calculate the concentration of potassium iodate solution in grams per dm. We have to divide the moles from above, so 0.000403 divided by 0.0250, which gives us 0.0161. And then in order to get that in grams, we have to multiply this number by the molar mass, which is given here. So 214 times 0.0161 gives us 3.45 grams. So that's our final answer. Let's look at the final part, which is D, which is the preparation. So again, you'll be given a student brief and you have to follow the instructions to prepare and sometimes purify an organic or an inorganic compound. And so the techniques you might be doing are distillation, heating under reflux, filtering, purification, solvent extraction, drying, or crystallization and recrystallization. So I'll talk about the two most common ones, which are the preparation of either a simple or a double salt. So to prepare a simple salt, so most likely you'll be asked to do a copper 2 or a nickel 2 sulfate. So the procedure would be you'll have a solid, you will add that solid to a known volume of acid and you will heat it. And you'll keep adding the solid until it's in excess, meaning that you'll have a little bit of a precipitate in the solution. You will then filter the solution into an evaporating dish, and you basically leave that to crystallize, and usually on the next day you can then weigh the crystals. So I've got at the bottom here I've put what copper 2 sulfate crystals would look like. They'll be blue. You will often be also asked to describe them, so the most common way to describe them would be to give the color, so you just say blue, and they'll look like diamond shaped or rods. So you just say that they're blue and diamond shaped or diamond like. So this is what it's like to prepare a simple salt. You might also be asked to prepare a double salt, and a double salt will usually be hydrated ammonium iron 2 sulfate. And it's pretty much the same as a simple salt, other than that you're preparing two solutions. So the first solution you'll be preparing will be the iron 2 sulfate solution, and in this case you will be using iron filings of a known mass. You will be adding them to hot dilute sulfuric acid. And then for the second solution you'll be preparing ammonium sulfate, and you'll be using dilute ammonia and add it to dilute sulfuric acid until it becomes alkaline. Once you've prepared both solutions, you will mix them, and you will then let half of the water evaporate, and you'll transfer them again into an evaporating dish and let the crystals form. And here on the left, I have an example of a hydrated ammonium iron 2 sulfate crystals, so they'll be sort of pale green. So in any question involving, so once you've prepared the salt, most of the time you'll be asked sort of to carry out these calculations. So first they'll ask you to calculate the molar mass of the reactant that you measured out. Then you'll calculate the moles. So to get the moles, you divide the mass by the molar mass, and you'll get the moles of the reactant. Then again, you look at the balanced equation to see what the moles of the product are, like we did in the previous example. So they can be either 1 to 1, meaning that you have the same number of moles of product and reactant, or it could be 1 to 2. So you just have to look at the balanced equation. And most of the time you'll be asked to calculate the percentage yield. So to get the percentage yield, you will have to divide the actual mass of the product by the theoretical mass. So the actual mass is, when you weigh your crystals, that will be your actual mass, divided by the theoretical mass, which you will calculate, times 100, and that will give you the percentage yield. And I thought it would be good to look at just one question. So this is a question here. So we are using a measuring cylinder of 25 centimeters cubed of 1 molar sulfuric acid was transferred into a beaker and the solution warmed. Then portions of copper 2 oxide were added with stirring until the base was in excess. The hot solution was filtered and the solution evaporated to halve its volume. The solution was left to cool. The crystals formed were dried and weighed in pre-weighted weighing bottle. So these are the results. The mass of the container and the hydrated copper 2 sulfate was 29.66. The mass of the empty was 24. So obviously minusing these two values from each other, we get the mass of, so this is our actual mass. So this is what we got after this preparation. So the first question they're asking is, one second. So question A, what was observed as copper 2 oxide was added? So we're adding the copper 2 oxide to the sulfuric acid. So we would be observing the solution would be turning blue, and there might be some frothing because it's reacting. So that's for A. B, what showed that the copper oxide was in excess? So again, that's something we talked about before. So to make sure that something is in excess, you keep adding it until you've got some precipitate that collects at the bottom. So it shows that the acid and the copper oxide have fully reacted. Question C, why must the solution not be evaporated to dryness? Because we're trying to get a hydrated copper 2 sulfate. So if we evaporate it to dryness, then the anhydrous salt will form, which is anhydrous, meaning that it has no hydration, meaning that there is no water. So that would defeat the point of the experiment. So question D, describe the appearance of the crystals. So again, we saw them on the previous page. They're blue. You can either describe them as diamond-shaped or rhombus-shaped. Either one is fine. So then question E is asking us to calculate the mass of the hydrated copper 2 sulfate that could be made from. So they're asking us to calculate the theoretical value. So to get the number of moles, so we get moles equals, so we get given the concentration and the volume. So again, concentration is 1.0 times, because 25 centimeters cubed needs to be in decimeters, so we need to divide that by 1,000. So we get 0.025 moles. And then to get the theoretical mass, we need to divide the moles that we've just calculated times the molar mass, which we also get given here as 249.6. So we multiply that by 249.6, and the mass we get is 6.24 grams, which is our theoretical value. So this is what we should get in theory if we follow this procedure properly. So the next question is asking us to calculate the percentage yield of the preparation. So to get the percentage yield, we need to divide the actual by the theoretical times 100. So the actual is 5.01 grams. So that's what we managed to make, which is 5 grams, divided by the theoretical, which is 6.24 grams times 100%. So we get 80%, and that's pretty good. That's very good. So we managed to get about 80% of the theoretical value. And the final question is asking, why is the yield less than 100? Well, because there's quite a few reasons you could put, but the most common ones is because some of the saturated solution did not crystallize. We could also have, let too much water evaporate, therefore we have some anhydrous salt that was formed. And also some of the solution might have been lost during transfer and filtration, so when we're filtering it, some could have remained on the filter paper, therefore reducing our actual yield.